let's go back to the handout that we've been working on. Come on. If my computer does something stupid, because it's been on for 2 days and I didn't know. All right, can everybody see my iPad?
Mm-hmm.
All right, we're going back to, excuse me, back to, where did we stopped here. So let's go ahead and look at the ester addition, because I want to really talk about that. I'm actually going to put this on a blank sheet, because it's more to it than meets the eye.
Is this doing a Grignard with an ester?
Say again, yes.
Okay, I remember, I think there was one part of the video that talked about this.
Yeah.
I don't think it finished.
Well, it did finish because you get a ketone, but there's a way to take that ketone and push it to an alcohol too. So I don't want to lose that point. So I'm gonna write this on a blank spot where I can have plenty of room to discuss it. Come on, there we go. And not on a line, because I saw my notes that I posted the other day, and they were cut off. So let me go to, so we had this ester. Come on. Is that right? Plus.
Is this one of the problems, or?
It's the same problem. I'm just writing it down here because I need more room.
Oh, gotcha.
I don't want to try to compress it. That's right. All right, so there's my Grignard. Here's my ester. So just like with the aldehyde, let me put a heading up here too. Right, so we're talking about addition of Grignards to ester. And so just like the ketone or the aldehyde is going to go through this tetrahedral intermediate, right? So none of that changes. So I'm going to put in the arrows here, right? All of that's the same, right? None of that changes. So what would the intermediate look like? What do you think? I'm gonna put some brackets down here so you'll know where we are. Keep the same, keep the colors consistent. This doesn't change, right? That's still the same.
It's just the bromine is going to be added. Well, that bromine magnesium is going to be added.
It's like this, right?
Mm-hmm.
Is that right? And then I have a OCH3, and then this carbon right here from that alkene, the vinyl group, is what's getting attached. Like so. Yes or no? You know oxygen is going to be negative, right? And then the MgBr is positive. Let me put some way to split this up. All right. So with that intermediate, right, you could quench it, but most of the times the elimination is going to happen before before proton transfer. So this is going to happen. Right, so you end up losing the OCH3 group, and then you're left with a ketone. So that's the product. The main product is a ketone.
Wait, which group did you leave off?
The OCH3 right here.
Why?
Because that's okay, so let's think about it. if we added in the carbon group, the Grignard, if we did elimination and kicked it back off, no reaction would occur, right? So the OCH3 group is more susceptible to leaving.
Oh, okay.
Right, because that carbon, that vinyl group, that carbon, if it leaves and is negative, is not very stable. But the OCH, everything is based on the pKa of the conjugate acid. So if the vinyl group left, which is this group down here, if this group left, that would be bad. It's a terrible leaving group. So when this elimination happens, the OCH3 is a better leaving group. Right? So that's my product plus the salt, right? It's OCH3, MgBr. Following? Anybody not following? Say something. Because we got 22 people logged in and 2 people talking. Now 23.
I'm following.
Did we still follow the same like CR plus MX rule?
Well, this is different though, right? That was for the substitution.
This is elimination.
This is an addition.
Addition.
Right? So in an addition, the mechanism changes. So you can't use that same, I guess it would be a paradigm. You can't use that same paradigm to explain these additions. Substitutions, you can use it all day. Are we following that? Is that okay?
And we got the CH3 and all that at the bottom, that left because of the pKa.
Right, because when you do, so this is an elimination. Right, the difference in elimination and substitution is in elimination, you always make a pi bond. It's either gonna make a excuse me, a double bond or a triple bond, but you always make a pi bond when you eliminate. So the pi bond came right here, right? When I made that CO pi bond.
Right, okay.
And then the leaving group happened to be the OCH3.
Oh, okay.
So if you take here's the point I'm trying to make or trying to get to. So, and ester, you got the mnemonic, right, from the video. A Grignard plus an ester or equals a ketone. You remember that? So if you add a Grignard to an ester, you're going to get a ketone if you only add one equivalent, if the ratio is 1:1, right? If I add another Grignard, let's say, y'all want to use the same one or use something different?
Could you use
the same one just for
same one, just for continuity? All right. So this is the same Grignard. What's going to happen if I take this Grignard right here and add it to this ketone up here? And then follow that up with, so this will be 1, and then 2, I'll quench it with H+. What should I get? Grignard plus an aldehyde or a ketone equals what?
Alcohol.
An alcohol, right? So we've already seen that before. I'm not going to go through the arrow pushing. I'm just going to draw the product and show you what we should get.
I think I see it.
OH.
Yeah, OH.
That'll be there, and then this will be here. Right in those methyl groups, but I'm stuck. Right, so this would be the final product, right? And then plus whatever side products you get from the leftover magnesium. But the point is, if I have a Grignard, let me say this a different way. If I have an ester plus 1 mole of Grignard, then I'm going to get a ketone.
What if you have 2 moles? Or is that ever a case? Will you ever have 2?
Yeah, that's what we did here when we added the second Grignard. it took the ketone all the way to the alcohol.
Oh, you added. Oh, that's when you added it. Okay.
Right. So let me put that over here and kind of emphasize it. So this is the second mole. I'm gonna say. Right. So that's your second.
Didn't we do this? The same thing. That was on Wednesday as well.
Mm-hmm.
Okay.
All we were doing on Wednesday was taking aldehydes or ketones and adding a granule to it, and then quenching it with acid. But with an ester, you got a chance to, if you only add one equivalent of granule, you're going to get a ketone. But if you add another one, a second equivalent, then you can get the aldehyde. I mean, you can get the alcohol. I'm gonna write that down here too. So a ester plus 1 mole of granule will give you a ketone, and then an ester plus 2 moles will give you an alcohol. All right, any questions about that?
And that second product that was made, or those are just, what's on that double bond? That is the CH3.
It's a CH3.
Okay.
I just didn't have the space to write it out. It's the same that's up here.
Okay.
Yeah.
Oh, it's the two. Oh, okay. I was wondering why I was 2 for a second. Okay, those 2.
So I added one in this step right here.
And then one from the other.
And then I added the second one in this step. All right. Let's go back up to here. Where was it? Right here. Okay, great. Let's go back to here. All right. So what would the product be from this reaction right here?
Well, you drive the same thing, and then the Br bromine magnesium will be on with the oxygen. Well, not with. Well, yeah, with the oxygen.
So you want to show the intermediate first? That's fine. That's fine.
Wait, is that? Do you have to show the intermediate, or is that never?
Well, you'll show the intermediate. It depends on what the question asks. See right here where the question just asks, predict the product, you just draw the product. If it says propose a mechanism, then you'll show the arrows. But we're going to show them anyway because that helps. So this is going to attack here. Is that right? Break the CO pi bond. And so the intermediate looks like this. O minus Mg. Let me erase that. That's from a different problem. Br, is that right?
Yes.
OCH3. And then the carbon from that vinyl group, right? That's my intermediate. And then what's going to happen to that? It's going to collapse, right? It's going to break down and kick off the OCH3 group. Like this, just like we just did. So what do you have left?
Now it's going to become a pi bond with
right there, right?
C3H going.
And then this is attached to it. Yes or no? So it becomes a ketone.
Oh, question.
Go ahead.
That MgBr, is it not with the oxygen or it's just next to the oxygen?
It's a salt, right? Because oxygen is negative and magnesium is positive. So they just make a salt. It's just like NaCl, right? So the oxygen, let me put the charge on magnesium too, because I shouldn't have left that. That's positive. So it's an electrostatic attraction. It's not a covalent bond.
Okay, sorry. Repetition is key for me. You're saying they went together because of their charges.
Yes, it's electrostatic.
Okay.
It's just like if I had something like X negative and then Y positive. They're only together because they have different charges.
Okay.
Right? You remember from like Chem when you had like let me give an example, like magnesium 2+, and SO4, 2 minus,
Mm-hmm.
right? The only reason those things will be together as a salt is because one of them is positive and one is negative.
Okay, gotcha.
In G-Chem, you didn't show this part, right? It was understood
Yeah.
that when you wrote Mg
SO4.
SO4, it was understood that this was a polyatomic, right? And it had a -2 charge. That's why the whole thing is neutral.
Yes.
Yeah. And it
Go
understood.
back up really quick.
Go ahead.
Could you go back up really quickly?
Oh, yeah.
Finish writing.
Does the oxygen there have 2 electron pairs?
It's got three electron pairs on it. It's got 2 electron pairs on this side,
Mm-hmm.
right? And then when you give it that pi bond, now it has 3. That's why it's negative.
Wouldn't that violate the octet rule though? Because
No.
it would have just 3 plus.
Plus 2 from the bond. That's 8.
Is it not? So it's not bonded to the magnesium. It's just
No.
having a
That's what I'm
dipole.
just saying. It's a salt. It's negative.
Okay,
Magnesium is positive, so they're attracted to one another, but there's no covalent bond between them.
I gotcha. So when it makes the pi bond, it loses that negativity, and that's why the magnesium
Right.
goes away.
That's why
Gotcha.
the magnesium goes to find this oxygen right here. Right? Because that oxygen, when it picks up that pair of electrons from the sigma bond between carbon, it's going to become negative. So it's like OCH3. It's got 3 lone pairs, and it's negative. So that's where magnesium is going. Right? Because magnesium, anytime you're making salts, if you have an atom or a functional group that's negative, if you got a positively charged metal or some other atom, they're going to find each other.
Gotcha. Thank you.
Especially when you get to the step where you get ready to quench it, because you're going to have to add some water. So you're going to have a really polar water layer and a slightly non-polar organic layer. So they will find each other.
So with that OCH3, will we just have to know the pKa? Because I know you said that. No,
it's coming off. That's the only thing that's coming. The group that you get added in from the Grignard is not leaving when you do the elimination step.
So what's the difference between that one leaving and then the CH3 at the bottom, like that group?
Which group? Right here?
Yeah, I just want to make sure
This right here?
What's the difference?
Oh no. Let me show you the difference. This is good though. I like this. You know, I like talk. I like engaging. I
just want to make sure. I want to know the whys, like that.
So here's what you basically have. You got an sp2 carbon that's negative, right? if you're looking at the Grignard.
Mm-hmm.
You follow me?
Yes.
And that's going to be compared to a oxygen that's negative. Now, so what do you base how do you determine how stable those groups are? It's either hybridization, induction, resonance, size, or electronegativity, right? So when you look at the oxygen and the sp2 hybridized carbon, oxygen is more electronegative for one, and it's slightly larger.
Mm-hmm.
But the sp2 carbon, I'm gonna show you why this is bad, right? One of the ways to spread out charge is resonance, right? So the hybridization state doesn't matter. The induction is not in play because there's no other functional groups there to cause induction. And the electronegativity is the only thing that's left, right? Size-wise, oxygen is not that much bigger than carbons to say for that to be the only factor. So it's based on electronegativity, right? You can't do resonance because the negative charge here is basically perpendicular to the pi system in the double bond.
Right, yeah, I see.
So there's no overlap. That negative charge just on its own. So if you were to lose this group up here, and put a different color arrow, if you lost that, you'll be making a very unstable anion. As opposed to losing oxygen, where oxygen has an electronegativity of 3.5 and it can handle a negative charge very, very well. You follow me? So that's why when you eliminate That's why the oxygen is a better leaving group.
Okay.
Let me tell you, show it to you from a pKa perspective, right? So the pKa of this hydrogen is somewhere around 50. That's really bad. That's a terrible acid. And what that means is that if you pull that hydrogen off, what you get, the conjugate base, which would be up here with the carbon with a negative charge, is horrible. It's not very stable. Whereas the pKa of this, about 16. Not a great acid, but it's better than, it's, what is it? What's the difference between those? 34, 10 to the 34 times more acidic than the other one. You following? That's a huge difference. And that what that means is that the conjugate base, which is that negatively charged oxygen, is way more stable than the vinyl anion.
I got you.
Yeah, so that's why that's not going to leave. Once it attacks, it's not going anywhere.
Okay.
It's almost like taking a stray dog in. Like, boom, once you make that carbon-carbon bond, no, I ain't going nowhere. You done fed me. you got air conditioning. You gave me a bath. I ain't leaving. But the oxygen is more prone to leave.
Okay.
Does that make sense?
It does. Thank you.
All right. Let me go to a different, I'm going to get a blank sheet because I want to talk about the retrosynthesis. And then we're going to go back and work some problems dealing with that. All right. All right, so let's jump into this next topic for granular additions to carbonyls, which is retrosynthesis. And I'm gonna send you a video. I was supposed to send it yesterday, but I forgot. I mean, Wednesday, but I forgot. And I had all day to send it yesterday and didn't do it. Charge it to my head, not to my heart. All right. So what is retrosynthesis? Anybody? What does retro mean? Besides Jordans that came out 30 years ago.
Oh, well, you got me. That was my answer.
Yeah, it's actually working backwards, right? So a retrosynthesis is if you begin at the product and work back towards the start materials. Right, so you start with the product and then you break the product apart to its precursors. All right, let me give you an example. So if I started with, let's say I started with a double bond.
This is the product. Oh, wait, no, this is the
This
starting
is my product. And I want to know how I got there. But there's a bunch of ways to make double bonds. But I'm going to say that how do I want to put this? I'm going to say that's H2O, right? So the immediate precursor to that would be if I took the H and added it to one side and the OH and added it to the other side. Right, so let's do that. Let's say we started out with this. And then the H was here, right? That's a retrosynthesis. Start with what you have in the products and work backwards to figure out what the start materials are, right? So I could get from here to here by elimination. All right. So when you do retrosynthesis on granular addition products, right, you're going to start with whatever your precursor is or whatever your product is. Let's say we start with this. Like so, right? And then there's a hydrogen here, but it's, I didn't have to show that. It's because it's a skeletal form. All right. So the question is, if this alcohol came from the granular plus an aldehyde, what gradient and what aldehyde did we start with? That's the question. And there's a way to do it. There's a process to work backwards that I'm going to show you, and it's foolproof, right? It's foolproof. All you have to do is follow the process. You can take any gradient product and work backwards to the starting material, right? So I'm gonna give you the process first. I don't like doing this, but I'm gonna write it out, and then we're gonna show it mechanistically. So the first thing is remove H plus. All right, that's the first thing to do. Remove H plus from that gradient product. Handwriting, boy, I tell you. I'm gonna give me a handwriting coach. Remove H plus. Second thing you want to do is reform the pi bond. Right? So take off H plus, reform the pi bond, and then third thing is, the third one is arbitrary, but I'm gonna show you that there's more than one way to skin a cat, right? So you choose your leaving group. All right, that's the third step, choose a leaving group. So let's work through this example right here. I'm gonna redraw it because I don't wanna try to squeeze it into that little spot. So I'm gonna start here. Right. So here's a rule of thumb. Hydrogen is never going to be the leaving group.
Okay.
Never, right? Because you can't have a hydrogen gradient. You following? It's got to be a carbon magnesium bond. So your leaving group needs to have a carbon. Needs to be a carbon group, a carbon containing group. So first thing I want to do. Remove H plus. All right. So what would I get from that if I took off H plus from the oxygen? I should have said from oxygen. That's my fault.
Oh, from oxygen.
O minus.
O minus. Good. So I'm going to get that. I'm going to actually get that tetrahedral intermediate and Arnold. And let me put some electrons in here right quick. All right, so it's got three. That top lone pair is horrible. All right, so you got three lone pairs, negative charge. Now, fix this hydrogen too. Now, what's the next step?
Reform a pi bond.
Restore the pi bond.
Reform the pi bond. So when I do that, I'm going to have to, so 2 and 3 go together. So which part do you want to take off, right? That's why I say it's because you got two groups that you can choose from.
Oh.
The CH3.
Okay, let's do that. Let's take off the CH3. Let me fix this ring right quick.
Was it the rest we can choose which one we want to take off?
Yes. Yes.
So does it, so like say everyone right now we're gonna take off the CH3, but say if we choose to take off the H, it won't really make a difference.
Can't touch the H.
Oh, can't.
Remember just said that. And you agreed too. I heard you say okay.
I know, yes. Oh, I see. Never mind.
You can't have an H gradient, a hydrogen gradient, right? But you can have a carbon gradient. You'll never see magnesium bonded to hydrogen. I mean, if you see it, that magnesium is going to be ineffective. It's going to be unreactive. All right, so we're going to put the pi bond back in. Which leaving group? Because steps 2 and 3 go together. Reform the pi bond, choose your leaving group. So let me fix this too, because I'm going to post these notes. So you take H plus from the hydroxyl group. Which group do you want to take off? You said the CH3? I heard somebody say that.
Yeah, the CH3.
Yeah, carbon.
Boom. All right, so let's do it. So we're going to put the arrows in like so. Here, boom. That's going to put my pi bond back. And then boom, this is gonna kick off my CH3 group. Everybody okay with that?
Yes.
Look at where my arrow came from. I got an arrow coming from oxygen, from a lone pair on oxygen, and I have an arrow between the carbon-carbon sigma bond right here. That's really important. That's where the electrons are coming from. Where you start your arrow and where you stop it is very, very, very important. All right, we okay with that?
Mm-hmm.
What should I get from that?
It's gonna be.
I get
It's gonna be a double bond with hydrogen.
So I get an aldehyde. Is that right?
Mm-hmm.
Plus what? CH3 minus. Is that right?
Mm-hmm.
And then you already know because this is negative, that's what my granular is gonna be. Right. So I'm just gonna and then I can just put whatever halogen I want. It's up to you. You can stick a bromine on there, iodine, chlorine, it doesn't matter. Right? This is the precursor to the granule.
Wait, is that an arrow under the CH3?
It's not a reaction arrow though. It's just pointing.
Right.
It's a what's called a implied arrow, right? So that is implied that CH3 is going to become your granule that reacted with this aldehyde.
Okay.
So that's a granule precursor. Oh man, I need a big whiteboard. So that's the precursor to the granule. That lead the whatever group you kicked off, that's the group that's going to become your granule. Does that make sense?
Yes. The CH, it's just the CH3.
Yeah.
Not when it becomes the Mg. Okay.
Yeah, it can't become it, but once I get to that stage, I know that that's what I added to that aldehyde. So I'm assuming that was my granule. Are you following?
Yes.
Yeah. So could I do that a different way? Because you see, you got two groups you can kick off, right? Because you could also kick that ring off.
Yeah, you can do that.
Yeah, I can do that too, right? So we're gonna work some examples. I don't want to do it here because I don't want to confuse you, but we're gonna work some examples that ask you to show two ways that you could synthesize an alcohol or something like that. All right, so let's do that.
So question, how come you can't kick off that oxygen? Is it gonna bring us back to what you were saying earlier, like it'll be a bad acid or something?
No, the oxygen itself, okay, so keep in mind what we're doing. We're adding granules to carbonyls. Mm-hmm. So if I kick the oxygen off, I won't have a carbonyl in the start material.
Yeah, true. Okay.
Yeah, I can't. The only thing I'm removing are the carbon groups, because those are the groups that can be bound to magnesium in a granule reagent and added to a carbonyl.
Mm-hmm.
Let's do some examples, because I think it's clicking. I love Fridays. Let's do this example right here. And then we're gonna go down and do another example at the bottom of the page. Right, so you can see right here, it's giving you the granule, right?
Mm-hmm.
Mm-hmm.
It's giving you the granule. So your task would be to figure out what carbonyl the granule was added to. All right. So how will we do that? What's the first thing you want to do?
Take off the H.
Take off the H from OH. Is that right?
Mm-hmm.
I'll make sure I got the right number of carbon. So this become O minus. Is that right?
Yes.
Mm-hmm.
Now, based on the granule that you have over here, I want to see how you're thinking now. I need y'all to use some logic. Which group is coming off? when I put the pi bond back in.
The carbons to the left.
On the left, the allylic side.
Mm-hmm.
Okay, great. See, I knew it. I love Fridays. So we're gonna do this, and we're gonna do that. Is that right?
Mm-hmm.
What would that give me?
Is it aldehyde?
Yeah, great. It's an out. So you're gonna get this. I'm gonna keep it just how it looks too. So I don't want to confuse you. That is a CH3. Come on, Russell. Right, this group right here is a CH3. Everybody okay with that?
What you mean where the arrows removed? I mean where the
the carbon right here that I got highlighted in green.
Yeah.
The end of every
But
line.
what happened to the oxygen?
What oxygen? Talking about this one right here?
I mean, not the oxygen, I meant the hydrogen.
What
That's
hydrogen?
the first step. You had to remove it.
Oh no, that's gonna. Okay, so let me kind of go back and fix that. The hydrogen that's on oxygen came from an acid, right?
Mm-hmm.
In this step right here.
Oh.
So if I pull it off, it's just going back with whatever the conjugate base. But that's not the point. The point is I need to get rid of that so I can make oxygen negative. It's just a step in that process. It's not meant to be. This is not we're not doing the reaction in reverse. You follow what I'm saying?
Mm-hmm.
So I really don't. It really doesn't matter like where it went. I want to take it off so I can get that oxygen to be negative. It's just a way to think about how to work backwards with these granular products.
Wait, you said you're not
how
doing.
do I know which oxygen to kick off and to leave? I'm confused.
Say again, which hydrogen to take off?
Yeah, I mean hydrogen. I don't know why I keep saying oxygen.
That's all right.
Which
This
hydrogen?
one, it's always going to be the one on the OH group.
No, I'm saying because before you said that hydrogen is not a leaving group, so you was like, do not touch that hydrogen in the last.
Yeah, no, I didn't touch any of the hydrogen. Yeah, I didn't touch this one right here, which is on this carbon right here. It's not shown because it's skeletal.
Okay.
That you can't touch that one. So I'm just plucking off the OH proton to make oxygen negative.
Okay.
All right, that's my process for working backwards. Make oxygen negative, put the pi bond in, and break one of the carbon-carbon bonds.
We left off that group that was to the left.
Say again?
As one, I think, didn't someone say we left off the group?
Oh, I haven't drawn it in yet.
Okay.
So it'll be this aldehyde. Everybody agree with that? Because that's what we get when we pop off this part right here. This is what's left. Those are the two fragments that's left. That plus let's see. Yeah, that's right. Plus that. Is that right?
Mm-hmm.
Wait.
Again, don't lose sight of the fact that we are working backwards. We're starting with the addition products that we get if we put the granular and the carbonyl and adding them together. And we're working backwards to see what carbonyl and what granular we put together to get there. All right, so don't lose sight of that.
So the purple and the blue, those are two separate.
So this is what would be in this space. You see how this space over here is blank?
Okay.
Those would be my two reagents. It would be this aldehyde. I'm just going to keep the colors consistent. All right, it would be that aldehyde, H, right, plus this granular, right, which was given up here.
Right.
That's how I know what granular I'm starting with. I just needed to figure out which aldehyde I was starting with.
Oh, because the green and the aldehyde make alcohol.
Yeah, exactly.
Okay. It's just
so we started with the alcohol and we worked backwards to the granular and the carbonyl. And remember, when we first started talking about this, you can see that the alcohol it's a secondary alcohol. So that means it had to come from an aldehyde and a granular. If it was a tertiary alcohol, that means it came from a ketone and a granular. That's it. That's somewhere in your notes. Somewhere. All right. Any question? More questions? It's Friday now. Y'all loosen up. Don't be scared.
You late.
You already scared?
I never liked. Organic chemistry is very intimidating for me.
Tell yourself it's not. If you tell yourself it is, you're gonna keep believing that. It's not intimidating. It's all about learning how to compartmentalize the information. It's a lot of information, but it's all broken down into different topics. Right now, the topic is retrosynthesis of granular products.
But sometimes topics, they start like, crossing each other. And
Sometimes. That's when you start connecting dots and you realize that two topics are not necessarily that different from each other. You'll get it. It's going to come. It just takes time and repetition. And you're going to have to start thinking about how things are related. You definitely don't want to keep everything in separate boxes when there's always some commonality between the topics. But when you first start out, it's good to compartmentalize it until you can, reach that barrier between topics. Let's do another example. I like this. I like y'all. This is a good class.
Can you go back up, Dr. Russell, before you start? That dark purple right there with the two lone pairs. Is that
That's the result of this step right here.
the result?
Right. Remember, whatever I get, whatever carbon group I kick off, that's going to be my granular precursor. All I need to do is just stick a magnesium on there.
Oh, you stuck the magnesium there. Okay.
Right here.
Right. Okay.
Yeah. And it even gave us the granular up here. All we had to do is figure out what carbonyl they added to.
Okay.
That's how we knew which piece to break off in the retrosynthesis.
I'm still confused.
Go ahead. Ask whatever you confused about. Go ahead and ask it. I'd rather you ask it now than miss it on the test.
Okay, so that blue and purple on the left, are you just showing how it combined to cause that dark purple that you circled?
No. You're talking about these two things right here?
Yeah.
No.
Those get the product.
Let me back up. Okay.
Those are the three.
We have I'm about to erase some stuff. I'm erasing all of this. We have a product, yes? We don't have star materials. Yes? So the goal is to perform what we call a retrosynthesis, or to work backwards. That's what we're doing. So we have the product. We want to know what the star materials are. One of our star materials is given right here. Is that right?
Yes.
And then what we did on the other page was show how to work backwards. First thing you want to do is take off the proton from the OH group. So that's going to get you back to your intermediate. Is that right? Is this not the same intermediate that we've seen in all of our examples? Where oxygen is negative. Is that right?
I see it.
So now we at the intermediate. Now we have to have two more steps to put the pi bond back in and to break off one of the carbon-carbon bonds. But the fact that you already know which one to break because you got the granular right here, then that tells you how to push your arrows from the intermediate to your two precursors. You following that?
Yes.
So when I put the pi bond in and I break the other carbon-carbon bond, this is what I'm left with right here. These two things.
Mm-hmm.
Are you following? So those are, this is one of my start materials, which I just redrew over there. And then the other one is the precursor to the Grignard, which we already had. So I just redrew that over here.
Okay.
Right. Keep in mind, we're working from product back to starting materials. We're gonna do another example and it's gonna click, I promise. Let's go down here to these ugly problems down here. Let's see what we got. Yeah, right here. All right. So this problem asks you to propose three ways, right, to work backwards to start material and product. All right. So let me give you a head start. You're gonna start with the intermediate. Okay, that's what I'm starting with. The question is, what can you do to that? How many ways can you break that down?
3.
One,
Just triggered.
3.
You really got 3 different ways, right? Because you got a tertiary alcohol, which means your start is going to be a ketone, and plus a Grignard. So you got this group, and then you got this group that you can take off. Is that right?
All right.
So I took off the H plus. Now what do I have to do?
Make a pi bond.
Put the pi bond back in and pick which group you want to knock off.
Do the one to the left, the first one.
The ethyl group?
Yes.
All right, so I'm gonna do that. Is that right?
Mm-hmm.
Keep in mind, at the end of each of these lines now, those are CH3s, so don't panic about that.
Right.
So this group that I just kicked off, I'm gonna do this, right? I have this. Is that right?
Yes.
That's left. Plus this. See, this is, I'm gonna write it out. That's a CH2, CH3, and the CH2 is negative because I gave it a pair of electrons. Yes or no?
Yes.
Okay. Which one of those is going to become the Grignard? It's the ethyl group. Is that right? This group.
Yeah, the ethyl with the 2CH.
All I got to do now is stick a magnesium on that carbon, and that's my 2 start materials. So the way I would write it would look like this. I'm going to write it right up in this little gap. This plus CH3, CH2,
Mg.
Br will give me this.
And this is just one way.
That's one way. But then you got other 2 methyl groups that you can knock off and do it. You following?
Wait, say it again.
See the other 2 groups that are on there? We had let me change the color of the highlighted. God dang it. I'm trying to do that. So I'm gonna highlight this one in yellow. I'm gonna highlight the other one in blue. You feel me? You can do the same thing, but just knock off a different group.
So, like, say if we did the one in the blue, with the, can you knock off the ethyl group or?
You said you want to do the blue one, right?
Right.
So we could do this and then that. You following? And so over here, instead of it being an ethyl group, it would be just a CH3. And that's negative. Yes or no?
It would just be, it would just be plus CH3.
And then if I wrote out the equation, it would just be CH3 MgBr. If I took that and added it to this ketone, then the ketone would change because what's left would be this. Is that right?
Hold on. Wait. Oh, wait.
Yeah, because if I took this off right here, then the ketone is going to change.
Double bond. Okay.
I'm gonna draw it down here. Is that right? Because the two groups left.
Yes.
Ethyl and the ethyl.
Yeah, I see it.
Yeah. And if you knock off the other methyl group, the yellow one is going to be the same thing. Is that clear? No? Yes?
Yes.
Let's do it. Let's do a harder one. Let's do D. And I'm gonna redraw it down here in the blank space because I don't want to compress it and have it looking all junky. I'm gonna do it down here in the blank space. I think it was like this. Was it? Fix my weight. And it asks for 3 ways, right, to retrosynthetically break that down. So you want to go from, this is your product, and you're trying to go to the star materials, where the star material is a granular plus a carbonyl, right? Is that right?
I thought it was. If we have an alcohol,
Mm-hmm.
it can also be a plus a carbonyl.
Okay, so this is my product, right? This is the end product, which is an alcohol. And I can make alcohols by doing what? Adding a granular to either aldehyde or a ketone. Is that right?
Yes.
Yeah. So that's what I'm working backwards. I start with the alcohol, and then I'm working backwards to get to the granular and the carbonyl that I added together to make it.
Okay.
Is that okay?
Mm-hmm.
We only got time to do one, but I want you to work on the other ones, and then I'm gonna send you a video tonight or today, and then on Monday we're gonna work some more of these, and we're gonna move on to another topic.
I need this lecture video.
It's recording, and plus I'm gonna send you a real, like a video with all the details and all that stuff in it.
Okay.
All right. So what's the first step? How do I approach these problems? What's the first thing I need to do?
Move that proton.
Take off the proton and reform that intermediate. Is that right?
Mm-hmm.
So this is what the intermediate is gonna look like, right? Boom. It's gonna be O minus. I'm gonna put my electrons in, like any good chemist would.
Never put my electrons in.
Right? Should. It'll save you a lot of grief. I'm just gonna put a circle in here. I don't feel like drawing all those double bonds. That's another way to draw it, by the way. It's called a Kekulé structure.
Never heard of it.
That's all right. We're gonna study aromatics. They're coming up actually in the next few weeks. All right. Now what? Pick a group.
The aromatic ring.
Look at that. That's some extravagance right there. Take off the best group. Right? So that's what we're gonna do. So what 2 fragments are we left with? We're left with a ketone that looks like, sorry, hold up. That looks like this, right? Is that right?
Mm-hmm.
Plus what?
That one.
Excuse me.
Bless you. Plus that. Yes?
Yes.
And then this is what? This is my granular precursor. Is that right?
Mm-hmm.
So I can actually go ahead and write that as a granular. Boom, and I'm done. That's one way to make that alcohol that we started with up here. Is that right?
Mhm.
Let me tell you about the lowercase r's and this touch screen. That's one way. Now, can you see the other two ways? What you're going to end up doing? Right, you got a piece
Yes.
of here that you can knock off. Is that right? And then you got this methyl group down here that you can knock off. So that's where your other two pathways are going to come from. And no matter which three ways you add the carbonyl and the green together, you're going to arrive at that alcohol up top. Right? Is that all right? Keep practicing and don't stop because it's Friday and it's late.
That's all right.
Get you a hamburger with some Lysol on the aluminum foil. Come on back and there's some more problems. All right, we're gonna stop sharing anyway. Any questions?
Not right now. I need to freshen up on alkenes and aldehydes and all that stuff. Because sometimes you be saying that's like a alkene or something, but I don't know what it looks like to identify.
There's a double bond.
Let me think. There's a chart in your book. I think it's in either chapter 2 or chapter 3, dealing with functional groups. You need to go back and look over that chart. It's got all the functional groups. Aldehydes, ketones, esters, amides, amines, sulfones, everything. Alkenes, alkanes, alkynes, everything is on that chart. I think it's in chapter 2 or chapter 3. Yeah, those functional groups will trip you up because that's part of.
I think that's the only thing that's pushing me back because it's challenging to identify them to even start the equation. Yeah.
But that's part of speaking the language. Once you learn the functional groups, then now you have a different way to talk about stuff. Definitely need to go back and look at them and refresh.
Okay.
All right. Any questions? Any other questions? I'm about to send this. I'll upload this to YouTube, and I'm also going to send you a retrosynthesis video to watch to reinforce what we did today. So on Monday, you should come back swinging.
Cool.
Because we're going to work through some more of those problems.
Wait, Monday we don't have class.
We won't have class?
You mean Wednesday?
Yeah.
Nope.
Oh, yeah.
Labor Day weekend. 3 days.
Hold up.
You be on Zoom confused. You telling us like where y'all at?
On Monday, I'm just tripping. Y'all ain't even got to come nowhere. Just keep your pajamas on. The fire is hot, man. What is that?
See you on Wednesday.
See you on Wednesday.
God dog it. Y'all, I don't know no more.
God is good all the time.
Yeah. After you do it, I told you last night. Oh, sorry about that. That's my son.
Is the exam still scheduled for this Friday?
We could do, it won't be a lot. It would be what we're doing now, organometallics. What did we do when we finished, what was the first thing we started on? Was it this?
Yes.
Yeah, it'll probably be just some questions on that. I still want to keep it because I want to get.
This Friday or next Friday?
It wouldn't be this Friday because we just started this on Monday, right?
Yeah.
It'll be the next Friday.
Okay.
Yeah. It's instead of every 4 weeks, it's every 2 weeks. I like that though. It keeps you from procrastinating.
Yeah, it does.
Even if it's a short test with only a few questions from 2 subject areas, that's better than taking a long test with a bunch of stuff and then trying to study it all in a couple of days before the exam. So that's what we're going to do. We're going to keep it every 2 weeks. All right. If there's no other questions, I'm going to stop recording and I'm going